All right, welcome back. Good morning, everyone. So let's just quickly recap what we talked about yesterday. So we talked about just how do quantum algorithms work in general? Why do we hope to see any speed ups from them? And we saw that they're this very strange creature that tries to do something faster by exploiting constructive and destructive interference among exponentially many amplitudes. Okay, and if you don't see that happening, then in some sense, we are not seeing a quantum speed up. Right, so we have the task is left to us to figure out how to choreograph the right kind of interference pattern for whatever problem we care about. Okay, and then we talked a lot yesterday. Can people hear? We talked a lot yesterday about the distinction between computational and query complexity. Right, computational complexity is measuring typically the number of gates in a quantum circuit to compute some function. We're often interested in the minimum number of gates in any possible circuit. Okay, with query complexity, we just imagine a black box that computes some function f, which might have an enormous domain. And we're trying to learn some property of f by making queries to it. The queries can, of course, happen in quantum superposition. And the only resource we're interested in, typically, is the number of queries. Right? We don't worry about the other computation steps. Okay, and look, there's no getting around it. The query model looks weird the first time you encounter it, right? And it is natural to say, well, look, in the real world, we ultimately care about how many, real gates our real quantum computer is going to have to apply, right? So why are we worrying about the number of queries to this hypothetical oracle that doesn't even exist? Or, if it did exist, if we wanted it to exist, we would need to construct it ourselves and then worry about its complexity. Okay, so what I really want to say about that is that, if you'll just have faith that the query, that this is a reasonable way to think about quantum algorithms, then by the end of this lecture, your faith will have been repaid. Okay, so yesterday we had time to see two quantum algorithms, two of the first ones to be invented. First, Deutsch-Jozsa. Here you're given a black box function f that maps 1-bit input to 1-bit output. And your task is just to compute the parity of f of 0 and f of 1. I think yesterday I wrote, f of x and f of y, which was not, it's f of 0 and f of 1. Okay, that was just a thinko. Okay, so interestingly, there is a quantum algorithm that will do this with only one query to f. Okay, so the quantum query complexity of parity is only half of the classical query complexity. Okay, then we talked about the Bernstein-Vazirani problem. Here you're given black box access or oracle access, they mean the same thing, to a Boolean function f that maps n bits of input to 1 bit of output. Okay, and you are promised that there exists a secret string s such that all that f of x is it's just s dot x mod 2, right? And inner product mod 2. And your challenge is to find s. Okay, classically we saw that n queries to f are necessary and sufficient to solve this problem. But then amazingly, we saw that there's a quantum algorithm that solves it using only one query, again, to f. Okay, and actually I didn't have time to say this yesterday, but Bernstein-Vazirani is actually a perfect example of the role of constructive and destructive interference in quantum algorithms, right? Because if you think about what's happening, right, we first create an equal superposition over all 2 to the n, possible strings of n bits. We then apply appropriate phases, encoding our function f of x, and then we do another round of Hadamard gates. right? What do those Hadamard gates do? Well, they create a gigantic interference pattern. Okay, and what happens? Well, I claim that for every string other than S, it receives exponentially many contributions to its amplitude, to its final amplitude, but half of the contributions are positive and half are negative, and so they all just cancel each other out. Okay, and it is only for S itself that all of the contributions to its final amplitude are all positive, right? So they just all add up, and then when you look at the end, you simply see S with certainty. Okay, I will offer it as another exercise to verify what I just said by an explicit calculation. Okay. Good. Okay, and then we did a little bit of complexity classes just to orient ourselves, and see, what kinds of problems could we hope to solve with quantum algorithms. So we saw P, which probably equals BPP, deterministic and probabilistic polynomial time. NP, the verifiable problems. P space, problem solvable with polynomial memory. Exp, problem solvable with an exponential amount of time, and these all fit into a pretty neat hierarchy. By the way, computer scientists can prove that P is different from exp. Okay, we at least know that for sure, right? From which it follows logically that either P is not equal to NP, or NP is not equal to P space, or P space is not equal to exp. Right? At least one of the three has to be true. Now, my guess, or most people's guess, is that all three of them are true. But what can you do? Okay, and then we talked about BQP, bounded error quantum polynomial time, the sort of quantum generalization of P, the class of decision problems that are efficiently solvable by a quantum computer, which is sort of, the main object of interest in quantum algorithms, to understand what is in BQP. Okay, and and that's sort of off to the side somewhere, a little harder to classify, right? It sits inside of P space for sure. It contains classical BPP for sure. Its relationship to NP is not known. It may very well be incomparable. Okay, questions? Okay, good. So we've got a lot to do today. And what I want to start with this morning is, I guess some of the all-time greatest hits of quantum algorithms. Okay, and we're going to start with Simon's algorithm, which is again an algorithm for one of these weird black box problems that you say, where the hell did that come from? Okay, but this is the first quantum algorithm that solves a problem in polynomial time that provably requires exponential time for any classical algorithm. Okay, again, in the black box setting. Okay, so let's define Simon's problem. This is from 1994. Okay, now we're going to be given black box access to a function f mapping n bits of input to, in this case, n bits of output. Okay, and now we're promised again that there is some secret string s, right? So we're putting some structure on our function to try to, help a quantum algorithm see what's going on while still making it opaque to classical algorithms. Okay, so we have this string s, which is not the all zero string. Okay, and it's we'll think of it as the secret exclusive OR mask. Okay, and we're promised that f has the following property, that f of x is equal to f of y if and only if y equals the bitwise exclusive OR of x with s. Okay, so just to unpack this a little, what this is saying is that there is some secret subset of the n input bits, namely the bits where s is 1, right? Such that, if I take any input and I flip the bits in that set, then the value of f is unchanged. Okay, but if I flip any other non-empty subset of bits, then the value of f is changed. Okay, so f is a 2-to-1 function, but it's a special kind of 2-to-1 function where all of the collision pairs, if you like, the x, y such that f of x equals f of y, they all differ by this same hidden shift s. Okay, and the challenge is to find s. Okay, ideally using as few queries to f as possible. Okay, so let's first consider the classical case. How many queries do you think a classical algorithm would have to make to f in order to find s? Can anyone give me, let's say, an upper bound? 2 to the n, good. That will be an upper bound, right? In query complexity, you can always solve your problem by just querying everything, right? And then you're done. Okay, can anyone do a little better than that? Huh? N, how do you do it with n? Yeah, so classically, right, okay, so think about what happens with a classical algorithm, right? Well, what can it do? It can just pick a bunch of inputs one at a time and query them. So let's say it picks x1. It learns f of x1. It picks x2. It learns f of x2, right? But you might imagine that for a very long time, it's just going to see a whole bunch of distinct, random-looking values. Right, and then how much has our classical algorithm learned about s? Well, not a whole lot, right? I mean, it can rule out a few values of s, like it can rule out the exclusive OR of any pair that's already been queried, right? It knows that none of those are s, but other than that, there's still a whole bunch of a huge space of possible s's remaining. Right, so here's the question. Let's say that our classical algorithm is just picking the x sub i's randomly. Right, it's just randomly picking them. So when can the classical algorithm stop?
2 to the n minus 1.
Okay. Well, that would certainly be an upper bound on the number of steps that it could stop. But so I claim at what point has the algorithm learned s? Right. Well, it has learned s when it finds a collision, right? As soon as it finds some pair xi and xj such that f of xi equals f of xj, well then at that point it knows that s is what? Yeah, it's just xi plus, I'll just call this plus, bitwise exclusive OR with xj. Okay, so you could say, the problem sort of boils down to how long is it going to take until you see one of these collisions. Okay, so can anyone tell me sort of just probabilistically, how long would you expect it to take on average? Yes, yeah, excellent. So I claim that on average, it's going to require about 2 to the n over 2 queries. So the square root of the size of the domain. Why? Anyone? Yeah, right. Because what matters is the number of pairs, that we've queried, right? And then once that becomes of order 2 to the n, then then we've sort of explored most of the range, if you like. Okay. This is simply an instance of the famous birthday paradox. Right, which is not actually a paradox, okay, but is the fact that if you put only 23 people in a room, then there's a 50% chance that 2 of them have the same birthday, right? And in this room, surely there are at least several pairs of people with the same birthday. I'm not going to go through and do it, but you may have been in a lecture where that was done, okay? Because you don't need 3 of order 365 people, because what matters is the number of pairs of people. Okay, this is also a trick commonly exploited in cryptography, where it's called the birthday attack. Right? If you're looking for collisions in cryptographic hash functions, you only need the square root of the number of steps that you might naively expect. for exactly this reason. Okay, so by doing the birthday attack, we can solve Simon's problem classically with 2 to the n over 2 queries. Can we do it with fewer than that? Anyone? No? Does anyone have an argument for why not? Well, so there are some sort of tricks of the trade, for thinking about randomized algorithms, right? And one of them is to just say, well, look, we're trying, we have an algorithm. We don't know its behavior exactly, but we know that after t steps, it can have made at most t queries, right? It can have learned, f of x for at most t different values of x. Okay, and it can, sort of only stop, if at least if t is less than, 2 to the n over 2, then it can certainly only stop if it's found a collision, right? That would be the only way that it is uniquely identified S by that point, right? If we just imagine that f was chosen randomly, or with a random choice of S. Right? So then we just have to think about, well, how likely is it that a collision will have been observed within the first t queries? Right? And we can break that problem down further by saying, well, for every fixed pair, x sub I and x sub j, how likely is it that f of xi will equal f of xj? Again, supposing that f was chosen randomly. Anyone? Yeah, well, so we can say the probability that this equals that is actually going to be like 1 over 2 to the n minus 1, right? They'll be equal, if and only if, the exclusive OR of these two happens to be S, which just has a 1 in 2 to the n minus 1 chance of happening, right? So then after, so now we can use what's called the union bound, which says, if I'm interested in the probability that any of a whole bunch of bad events happens, it's at most the sum of the probabilities of each bad event individually, right? It's one of the most fundamental principles of the universe. Okay, like I use it, when I'm actually doing research, I probably use the union bound at least 20 times per day. Okay, so using the union bound, what is the probability that among the first t queries there will have been a collision? Huh? Well, it's the number of pairs, right? So we have to look at the number of pairs, right? Each pair is another event. So it's like t choose 2 divided by that. Okay? From which we conclude that until t is of order 2 to the n over 2, right, the probability of having found a collision will be small. It will be little l of 1. Okay? And that rules out a super fast classical algorithm to solve Simon's problem. I mean, you can be more rigorous about it, but I think that's a perfectly good physics argument. Okay. Okay. Oh, I can't. Okay. Then let's. There we go. Okay. So now let us see a quantum algorithm, namely Simon's algorithm, that solves this problem using only O of n queries. So an exponential improvement. Okay, so how does it work? Well, we're going to start, in this case, with 2n qubits, right? So n qubits for the inputs x, and another n for the outputs f of x. Okay? Now, how should we start our algorithm? Yeah, let's Hadamard everything. See? Okay, good. Now we've Hadamarded. What should we do next, anyone? Let's query. Yeah. Let's just make a query to f. In this case, a query means, we take f of x, and we just exclusive OR it into the second register. Okay? Now what should we do next? Let's do another round of Hadamards. Yeah, it seemed to work last time. Okay? And then we're going to just take each of these qubits and we're going to measure them in the 0, 1 basis. And then this is the entire quantum part of Simon's algorithm. Okay? And the whole rest of it will just be to understand what this is outputting and what clues does it give us about S. Okay? So let's look at what is happening in terms of the quantum state. Okay. So initially these Hadamards put us into an equal superposition over all 2 to the n bit strings. Okay. Then we in superposition query f of x. Okay. And then something interesting happens, or rather doesn't happen, that I want to call attention to. Okay, which is the entire results of the query. We can now throw them in the garbage can. Okay, we never even have to look at f of x. Okay, that's weird. Why did we even bother to query f if we're not even going to look at the answer? Right? That would make no sense for a classical algorithm. Right? What was the point of querying f? Huh? Yeah. So all we care about is the effect that making this query had on the input register, on the x register, right? Because these 2 registers are now entangled, right? And we care about what making this query did to the state of the first n qubits. Okay? This is actually common with quantum algorithms, right? That the reason you make a query is just to get the appropriate effect on the input, and you don't even care about the output of the query. Okay? Weird. All right, so we throw this away, and then but then let's just imagine that for convenience, that we fix a particular value of f of x, right? Because it might as well have been measured. For all we know. Now, if f of x is fixed, then what is going to be left in the first register? Anyone? Yes, perfect. What we're going to have left is an equal superposition over 2 inputs, x and y, such that f of x equals f of y. Okay? Okay, and now, what we, so it's not immediately clear. If we just measured this right away, we would see either x or y, and that would be useless. That would tell us nothing about the relation between the 2. Okay, but what we're now going to do is we're going to use the second round of Hadamard gates to choreograph an interference pattern between x and y. Okay, and this interference pattern is not going to immediately reveal S, but it will tell us something about S. Okay, so let's see what happens. Okay, so now we can reuse a result from yesterday that talked about what happens if you take a string x and you just Hadamard each of the n qubits. Okay, and if you'll remember from the Bernstein-Vazirani algorithm, what happened was you get an equal superposition. Let me say over all z, but with a phase. Okay, and the phase is equal to -1 to the x dot z. Right? This is what Hadamarding all n of the qubits does. Okay, so by the linearity of quantum mechanics, it follows that if I take a superposition over 2 strings x and y, and I Hadamard all n qubits of that, as Simon's algorithm is doing, then I'm going to get an equal superposition, I put another 1 over root 2 into the prefactor here. Sum over all z of what? Anyone? Well, it's just, by linearity, it's just I have a minus 1 to the x dot z plus minus 1 to the y dot z. Z. Right? So I have superposition over all z's where each one gets this amplitude, okay? It gets one contribution from x and another one from y. Okay? So now the thing that interests us is which z's could we possibly observe if we now measure z in the computational basis? Anyone? Yes, exactly. If we're going to observe the thing, well then we better have constructive rather than destructive interference between these two contributions. Huh? Well, we could say minus 1 to the things should be just equal, right? And that will imply that the exponent should be equal mod 2. Yeah. Okay? So in order for the z to be observed, we need minus 1 to the x dot z to equal minus 1 to the y dot z, which implies that x dot z equals y dot z mod 2. Okay? Now, what is y? Anyone? Well, can we rewrite y in terms of x? Let's say it's x plus s, right? By the Simon promise. Okay, right? We know that we found a pair that differed by this secret XOR mask s. Okay, so we can write. Sorry. Yeah. This should be. I'm sorry. This should be a z. This should be a z. Yeah, that's right. Okay. Otherwise, this is fine. So we get x dot z equals x plus s dot z mod 2. Okay. Now, can anyone simplify this for me? Well, it turns out you may have to think about it a little, but it turns out this is just like an addition in a vector space. This is an inner product in a vector space. And what can we do with additions and inner products? We can distribute, right? It satisfies the distributive law. So this thing is just equal to x dot s x dot z plus s dot z. Okay, mod 2. Right? And now what? Now we just cancel this. Cancel. And we're left with the equation s dot z equals 0 mod 2. Okay? So in conclusion, when we measure, what we'll find is some string z, we don't know which one, but some string z that has an inner product of 0 with s. Okay? So, as I warned you, right, we weren't going to get s right away. Okay? But grant me that we've learned something. Right? This is already, how on earth would, would a classical algorithm have done that? Right? We've now learned some linear equation that s satisfies. That's pretty cool. All right, but what if you want to go further? What if you actually want to know s? Then what could we do at this point? Anyone? Yeah, we could just keep repeating this over and over. Okay, so just keep repeating Simon's algorithm from the start a whole bunch of times. Mm-hmm. Yep, exactly. We measure the x register in the 0-1 basis. Okay, in the computational basis. As I said, we no longer care about the f of x register. Well, yeah, that's right. You can do whatever you want with the f of x register. Okay, you can, put it on your wall as an ornament. Okay, all right. So, So now we're just going to repeat Simon's algorithm over and over. Each time we're going to see a different random z, right? So we'll see, like, we will learn that s dot z1 equals 0 mod 2. You know, s dot z2 equals 0 mod 2 for some other string z2 that we'll also learn, and so on. Let's say up to m. Okay. Where m is of order n. Okay? And now what do we do? Yeah, now the rest can be handled by the classical computer. Okay? We don't need the quantum computer anymore because this is just a collection of linear equations, right? You know, mod 2. And we can solve them using Gaussian elimination. Okay, and you know, one can verify, I believe it is an exercise for you, that once you have seen order n random such linear equations, then with overwhelming probability, the only solutions to them will be, well, there will be two solutions. What, anyone? The all zero string, which we discard, and s. Okay, and then you know s. So that's Simon's algorithm. Okay. So, you know, as I said, this was the first problem, the first black box problem that required exponentially many randomized queries, but only polynomially many quantum queries. Okay. Now you might wonder, you know, what does, you know, so that sounds impressive, right? That's an exponential, you know, separation. But you know, but again, this is query complexity. So you might wonder, well, what does this mean in terms of complexity classes, right? Does this prove that BPP is not equal to BQP? Anyone? No, unfortunately, no, because this is a black box problem, right? It's you know, it involves an oracle. Okay, but what you can conclude from Simon's problem is the following. So here's how complexity theorists would state the conclusion. They would say there exists an oracle A relative to which BPP is not equal to BQP. So they would say that Simon's algorithm proves an oracle separation or a relativized separation between classical polynomial time and quantum polynomial time. Okay, meaning, you know, there is some oracle, right? And what the oracle will do is it will just encode infinitely many, you know, instances of Simon's problem, right? All of them randomly chosen, you know, with larger and larger values of n. Okay, that's all the oracle will do, right? And such that if I gave BPP and BQP that same oracle, well then, you know, the quantum computer would be able to solve all of the instances of Simon's problem, you know, efficiently in, you know, polynomial and n time. Okay, and the classical computer would surely fail for, you know, let's say, you know, at least half of the instances, right? It could hard code in the answers to some of them, but then after a while, it's just going to be guessing randomly because it doesn't have enough queries to solve them. Yeah.
Yeah. So how do we build the oracle? I mean,
okay.
In the oracle, we already assume we know the answer.
Yeah, but you know, the nice thing about oracles is that you can just, you know, construct them however you like, right? I mean, you know, all I'm claiming here is that this oracle exists. You know, I'm not claiming that it's like efficient to build it. Okay? And in fact, you know, this is a question to this day, right? We could, you know, once we know Simon's algorithm, we could then wonder, well, does this have any real world application? Right? Well, in order to find a real application of Simon's algorithm, you would somehow need to instantiate this oracle f, as we say, right? And that's actually a pretty stringent requirement, because you would need some kind of explicit function, you know, that first of all has the Simon behavior, right? It satisfies this promise. It has this secret XOR mask. Okay, if that's all you wanted, then that's not so hard to arrange. You could just do that by picking a linear function, for example, right? But, if it was a linear function, then, a classical algorithm could see that and take advantage of that. And, we would not have a classically hard problem, right? So you need to instantiate the oracle, by some explicit function, in such a way that, that the problem is still hard classically, even when you know that the function had that special form. Okay, this remains an open problem to this day. Okay, 25 years later, no one has found that kind of instantiation of Simon's problem. Yeah.
Instead of having there exists an oracle, we have for all oracles.
Mm-hmm.
A is equal to B.
Mm-hmm.
They conclude the truth.
Well, but that is not true. So sorry, you're saying if sorry, say that again.
I said that.
Yeah.
Forget Simon algorithm.
Yeah. Uh-huh.
Instead of showing that there exists an oracle.
Yep.
We showed that for all oracles.
Okay, but the problem is that that's not true. So, for example, if I let A be an oracle for a p-space complete problem, right, then I claim that BPP to the A and BQP to the A will then be equal. Namely, they'll both be p-space, right? So you can certainly make two classes equal with a suitable oracle. That's not so hard to do, right? So, but to make two classes different, you really have to find a black box problem that one class can solve efficiently and the other one can't. Yeah.
When you given oracle,
Yeah.
can you do it quantum oracle efficiently?
So if we know an efficient way to, like an efficient classical algorithm to compute A, then the answer is yes. We can also apply A efficiently as a quantum oracle, right? With, a polynomial number of Toffoli gates or whatever, right? And that was one of my exercises from yesterday to verify that. Yeah, David.
So I want to comment that this is a follow-up to our discussion yesterday.
Hmm?
There's work of Harrow and Rosenbaum
Okay.
a few years ago in which they introduced the model of randomizing,
Mhm.
internally randomizing the sum
Mhm.
of oracle.
Mhm.
And that actually provides both of what you were just saying.
Mm.
You have easy physical instantiation of the oracle.
Mhm.
It's very easy to have the randomization.
Mhm.
And maintains the quantum classical separation. In fact, it makes it infinite.
Mm-hmm. Oh yeah, thanks. So yeah, so I'm showing you the basics of but there are all sorts of ways that you can generalize all of this. You can consider quantum oracles, oracles that apply a unitary transformation, or as David pointed out, you can consider randomized oracles that might do a different thing on the same input, every time they're called. Okay, these are all interesting models to study. Yeah, was there another question? Yeah.
I was just going to ask, in general, how would this function, or how could you query superimpose to the oracle without having to load the data from each?
Oh, well, because again, so the oracle is a mathematical abstraction, okay? But so we just it's true because we assume that we can do that, right? But one could instantiate the oracle by having some fast algorithm that would compute A of x for any given x, right? If we had that, then that's what we would call an instantiation of the oracle. Okay, thanks. Okay, so actually, these are all good points people are raising, right? And well, what happened was that Simon wrote a paper. I think his goal was to prove that there were no interesting quantum speedups, and Simon's algorithm came out as the obstruction to that proof. Okay, and so he wrote up a paper about it, and it got rejected from the main computer science conferences. Why? Because this was just, a made-up, hypothetical oracle problem, and it clearly, has no real-world implication, right? It's just, in this weird oracle model. Okay, but the story goes that there was one guy who read Simon's paper and said, no, I think this is interesting. Okay, that guy was Peter Shor. Okay, and what Peter Shor said is that, well, if we just take Simon's problem and we change it a little bit, then we're going to get another problem that has small quantum query complexity and large classical query complexity. Okay, but for that other problem, there is an instantiation. Okay, and the instantiation of it is breaking the RSA cryptosystem. Okay, so I'm not going to have time to sort of fully present Shor's algorithm to you, but let me just sort of show you what are the main ingredients and sort of what is the same as Simon's algorithm and what has to be changed, and what is harder and more sophisticated there. Okay. Okay, so Shor is going to consider yet another black box problem. This one will be called period finding. Okay. And here we're given a black box function which now is mapping integers to integers. Let's say from integers from 0 up to q minus 1 to themselves. Okay, where you should think of q as being like exponentially large, right? Q is a very big number. Okay, and now we're going to be promised that there exists a secret number s, which is non-zero, okay, and which we will call the period. Okay, so such that f of x is equal to f of y if and only if s divides x minus y. Okay, so we're saying that f is periodic and it has period of s. Right, I'm promising you that. Okay, and furthermore, let's say s is less than the square root of q. Okay, that's a technical requirement. It has to not only be periodic, but it has to repeat often enough, within the range that we're looking at. Okay, excuse me. Yes. Yeah, it's right, and that follows from this if and only if statement. Good. Yes, good. Okay. And now our problem will again be to find s by querying f as few times as possible. Okay? Is this reminding anyone of Simon's problem? Okay. Good. Okay, so let's first ask, what is the classical query complexity of period finding? Anyone? Anyone have an upper bound? Yes, square root of q is an upper bound. In fact, one can even do better than that by using the fact that s is at most the square root of q, right? And remember that we can still do that birthday paradox. Right? As soon as you find x and y such that f of x equals f of y, well then you've learned something about the period. Either you found the period itself or you found some integer multiple of the period. Right? But you do that a few times, get a bunch of numbers, get a bunch of different integer multiples of the period. What could you do then? Yes, find their greatest common divisor. Does anyone know an algorithm to do that? Yes, Euclid's algorithm. So, like a priori, GCD seems like it might be almost as hard as factoring, right? But while factoring, as far as we know, requires a quantum computer to solve efficiently, taking the GCD of a bunch of numbers has an efficient classical algorithm that was known 2,300 years ago. Okay? The Euclidean algorithm, right? So okay, so So let's say, and we'll need that fact again. Okay, but let's say, classically, we can do it with something like square root of s queries. So let's say, maybe like q to the 1/4 queries. But one can show that that is essentially tight, right? That any class, for exactly the same reasons as with Simon's problem, that any randomized algorithm for finding the period will need approximately, this number of queries, which in particular will be exponential in n. Okay, so we again have a classically hard problem. Now, what Shor did, so his algorithm is really a combination of 3 different ingredients. Okay, the first ingredient is a quantum algorithm for period finding, which that, as it happens, makes only O of 1 queries to f. Constant number of queries. So it's even better than Simon's algorithm in that respect. Okay. Number 2, Shor shows that that algorithm is not only efficient in terms of query complexity. Okay, it also has it's also efficient in terms of the number of gates, right? So he can actually sort of realize, apply the unitaries that are needed for this algorithm with a polynomial in n number of quantum gates. Okay. And that's the famous quantum Fourier transform, right? Yeah.
You mean a polynomial number of gates?
Well, yeah. Okay. So there's actually 2 things here, right? There's a polynomial number of gates in addition to the queries, and then and then we will also sort of instantiate f, right, in such a way that f itself can be efficiently computed. Right? So we'll also give an efficient implementation of this oracle f. Okay, but and the question is, well, anyone could do that, but why do we care? Will this be an efficient implementation of f that we care about? Right? And so that brings us to the third point, which is that purely for classical reasons, having nothing to do with quantum mechanics, there is a reduction from the problem of factoring integers to period finding, with some efficiently computable function f, right? And this was kind of sort of known, but even this was not written down explicitly before Shor's paper. Okay. So let's actually start with the third step because it's cute. Okay, so the situation is, let's say we have this huge composite number. It's that's a product of 2 distinct primes, p and q. Okay, and we know n, and we are trying to recover p and q, and thereby read our enemy's email. Okay. So the question is, how can we reduce this to finding the period of a periodic function, which sounds like a completely different problem? Well, the key, so you start by just picking some random number x in the multiplicative group modulo n. Right? So, this just means the group of all the integers from 0 up to n minus 1 that are relatively prime to n with the multiplication operation. Okay, multiplication mod n. Okay, and then the crucial thing we do is we define a function, f of r, let's call it. F of r equals x to the r mod n. Okay? And the claim is that finding the period of this function f will enable us, or at least doing this for a few different choices of x, will enable us to factor n. Yeah?
Again, what's that symbol? The n?
That means the multiplicative group modulo n. Okay? It's the group of all the numbers relatively prime to n under multiplication mod n. Okay? It's a group. Right? It's what? It means what? Superscript is multiplication because it's a multiplicative group. Right? For example, the multiplicative group modulo 15, right, is going to have 8 elements. All right, exercise, verify that. Right, see what are the 8 elements. Verify that they form a group under multiplying them modulo 15. Okay.
Could you also just say pick a random x after that?
Yeah, right. Well, yes. If x happened to share a factor with n, well, then you're done before you even start. Right? Then you found your factor, and you're thrilled. You don't even have to turn the quantum computer on. Okay. All right. So yeah. So almost certainly it will be relatively prime. Yeah.
Instead, should it be fx?
No, it's f of r. Okay. It's a function of r. Okay. All right. That's going to be important. Okay. So now the question is, how does knowing the period of this help us to factor n? Okay. Well. So let's say that the period is s, right? So that would mean that in particular, if the period was s, it would mean that x to the s plus 1 would be equal to x mod n, right? So therefore, x to the s itself would be equal to 1 mod n, which means that x to the s minus 1 would be equal to 0 mod n. Right? Haven't done much. Okay? But now, let's suppose that we got lucky and s happened to be even. Okay? Then how could we rewrite this polynomial? Anyone? Could we factor it? Yeah. If s happens to be even, then we can factor this as x to the s over 2 plus 1 times x to the s over 2 minus 1 mod n. Right? And now, we could look at, the GCD of each of these guys with n, which, again, we can calculate by Euclid's algorithm, right? And it's possible that one of these guys is just a multiple of n, right? And if so, then we wouldn't really have learned anything. Okay? But let's grant me, let's suppose that we got lucky a second time. And neither of these things were integer multiples of n. Okay, then what would we learn from them? Yeah, well, if neither one is a multiple of n, well, then one of them has to be a multiple of p, and the other one has to be a multiple of q, right? And then when we take their GCD with n, then we're going to learn p and q themselves. Okay. So, so now, what remains is just to show that when you pick, you just keep picking x's randomly with a probability bounded above 0, like let's say, 20% or something, you will get lucky in these ways, right? These good things will happen. Okay? Verification of that exercise. Okay. Okay. So and now, furthermore, how but all of this would not be very interesting if we couldn't actually compute this function f efficiently. Okay, so how hard is it to compute f for a given r? Anyone? Well, you could do the naive thing, right? You could just take x times x times x times x, and r times, right? Is that going to be polynomial time? What? Yeah, right. No. If I had to multiply x over and over again, r times, then that would not be a polynomial time algorithm, okay? Because r can be an exponentially large number, right? But does anyone know what we could do that is more efficient than that to compute f of r? Yeah.
We could square it, and then square it,
Yeah.
square it until you get to the largest power of 2, which is smaller than that.
Perfect.
And then
Yes, perfect. Yeah. So there's a known trick in classical CS and number theory for exactly this situation. And the trick is called repeated squaring. Okay, and what it says basically you want to compute x to the r mod n, but do it really fast. Well, then you just basically decompose x to the r as some kind of expression that's going to look like this, right? It'll be some ugly looking thing involving, I square, that gives me x to the 2 to the something, and then I do another one and I get x to the 2 to the something else, right? And so forth. And in this way, when I multiply them all together, I can get like x to the 2 to the, let's say, k1 times x to the 2 to the k2, and so forth, which is just x to the 2 to the k1 plus 2 to the k2, and so forth. But now, any integer can be written as a sum of powers of 2. That's a fact that you may know, right? The binary representation due to Leibniz. Okay, so this is how we can actually compute f efficiently, and thereby efficiently instantiate this particular oracle, right? So this is actually, this x to the r mod n. We're now taking the black box, and I'm telling, we're telling you how to do it. Okay, so then what the next thing Shor does is gives a quantum algorithm that solves period finding using only a constant number of queries to f. Okay, and now we can go back to thinking about f as just an abstract black box, right? Because the fact that f of r is equal to x to the r mod n, that will no longer be relevant for us, right? All we needed from that was that it gave us a fast way to compute f of r. Excuse me? Yeah? Yeah? Yeah. So you keep repeating a few times until it happens to be even.
So it might happen that you need to do the evaluation of the period several times.
Yes.
Every time something is even.
Yes. As I said, you may have to repeat several times until these good events happen. And it is an exercise to show that you won't have to repeat that many times. Okay? 3 or 4 times would typically be enough. Okay? For just reasons of classical number theory. But, okay. Now, what we're going to do to solve period finding is basically just try to follow the steps of Simon's algorithm, as far as we can, and until we get stuck. Let's say. So we start by making an equal superposition over all of the integers from 0 up to q minus 1. Right? If I assume for simplicity that q is a power of 2, then this could be done by simply doing what to each qubit? Hadamarding. Right. Okay. And then in superposition, I'm going to evaluate f of r. In other words, query the oracle. Okay, and then just like with Simon's algorithm, I no longer care about this second register, right? I can throw it in the garbage. Okay, the only reason why I queried it was because of the effect that that query will produce on the R register. Okay, and so let's say that we fix some particular value of f of R over here. Then what is going to be left in the R register? Anyone? Yes. What will be left over is a superposition of the form R, sum over R, R plus S, R plus 2S, and so forth. I'm omitting the normalization, right? But what we'll have, right, is there will be some starting number, and then anything that differs from that starting number by a multiple of S is going to have the same value of R, right? By definition, f is a periodic function whose period is S, right? And so we're just going to get an equal superposition over some arithmetic progression. Right. Now again, just like with Simon's algorithm, we could measure this state immediately in the standard basis, but if we did, all we would see would be a random number that would tell us nothing about S. So if we want to extract useful information about S, then we'll have to do something more clever. Okay? And in this case, I confess that the next thing to do is not just another round of Hadamard's. Okay? It is, something that Shor had to invent. Which is called the quantum Fourier transform. Okay, so the quantum Fourier transform is just some Q by Q unitary matrix, which is defined like this, that its xy element is going to be 1 over square root of Q times e to the 2 pi I xy over Q. All right, so you can check, exercise, that this is a unitary matrix. This does define something unitary, and moreover, it is a type of Fourier transform. Okay, namely a Fourier transform over the group of integers modulo Q. Okay, and now, sort of, what is the point of a Fourier transform? And for any, there must be some engineers here who would, some electrical engineers who would know, right? Like, if I have a signal, what am I trying to extract from it by taking its Fourier transform? Yeah, I'm trying to extract frequency information. Well, what did I want here, right? I wanted frequency information. Okay, so it's no coincidence that we want to do a Fourier transform here, right? We're trying to extract information about the period. Okay, and so the goal of doing this is going to be to try to transform this state into a basis where then we can just measure and we will see something about S. Okay, and so there's sort of two cases here, right? To analyze what happens when you do this quantum Fourier transform, the best way to do it is first think about like a hypothetical easy case where it just so happened for some reason that the period S evenly divides Q. Okay, that probably won't happen in real life. Okay, but it will give us intuition for what happens in the general case. So if S divides Q, and I apply the Fourier transform to a state like this one, then what am I going to get out? Does anyone know? Well, it still doesn't determine which value I'm going to see, but it determines something about the value that I'll see. Okay? Yes. Excellent. I claim that if S evenly divides Q, then the result of applying the QFT is going to be a superposition over integer multiples of Q over S. Okay? Why does that happen? Exercise. Okay? And so then I can just measure that in the standard basis, and I'll get some integer multiple of Q over S. Like, call it KQ over S, right? Or actually, let's call it K1Q over S. Okay? So now, this may not be enough for me to immediately learn S. Okay? But now what can I do if I want to learn more about S? Anyone? Do it again, just like with Simon's algorithm, right? I could do it again, and now I'll get a different random integer multiple of Q over S. Call it K2Q over S. Okay? And K3Q over S. And so forth. Okay, now, with let's say a few of these numbers, like 3 or 4 of them, what can I now do? Huh? Take their GCD. Take their GCD with Euclid's algorithm, and then because these are all just random multiples, with overwhelming probability, before long, the GCD will simply be equal to Q over S itself. Okay, and now, well, I know Q, right? Because I picked Q, so now I also know S. Okay? So, okay. Another way to think about what's going on, again, every quantum algorithm can be seen in terms of interference, right? What the QFT is doing is it's creating a pattern of constructive and destructive interference where only the integer multiples of Q over S will enjoy constructive interference. And everything that's not an integer multiple of Q over S, will receive a whole bunch of contributions which are pointing every which way in the complex plane, right, in the unit circle or whatever, and they're just all going to cancel each other out. Okay, there. So I've already, I just did half of the exercise for you with that sentence, right? Just to verify that. Okay, now the hard case, or sort of you could say the real life case, is when S doesn't divide Q. Okay, as it won't in general, and then the Fourier transform no longer produces perfect constructive and destructive interference. Furthermore, you can't possibly just see integer multiples of Q over S because the thing you have to see has to be an integer, right? And Q over S is now not an integer, right? So what do you see? It turns out that what you'll see is a superposition over numbers that are close, that are mostly close to integer multiples of Q over S. Okay? And you can, try it for yourself with pen and paper and see that that's what happens. Okay? And so then what happens at the end is you get, with your classical computer, a bunch of numbers that are close to integer multiples of Q over S. Right? You know what Q is, and from these numbers you have to recover S. Okay? And so now this Shor does using another clever trick from classical number theory, which is called continued fractions. Okay? And if you want to know more, you can read about it online. Okay, and so then the final step was to actually give a small quantum circuit to implement this QFT, right? And so then the last thing you have to do in this algorithm is give a quantum circuit implements the QFT. It's easy to do it using like Q gates, but that's way too many because Q is exponentially large. What you want is a circuit that implements the QFT with something like log Q gates. or let's say log q to some power. I think what you can actually do it with about log q, log q gates. Okay, so polynomial in the number of bits that we're dealing with. Okay, and well, how do you do that? Well, how many of you have seen the fast Fourier transform, the FFT? Okay, yes, some of you. So so that's one of the most widely used classical algorithms that have ever been discovered, right? It's it lets you take a Fourier transform, of a vector of size n in only n log n steps instead of n squared steps that you would need naively, right? The QFT, the way you get a quantum circuit for it, is sort of to adapt the sort of recursion that's at the heart of the FFT. Okay, but here it's being done for a different purpose, right? So the QFT, in one sense, it is exponentially faster to implement than a classical Fourier transform is, right? Classical Fourier transform, you could do it for a vector of size n using like n log n steps. Okay, whereas in this case, we're trying to do a Fourier transform of a vector of size q using log q steps, right? Which is like, that's insane, right? That's like insanely efficient. But the downside is, this is this is like an ultra mega fast Fourier transform. It's not one where the answer, the Fourier transform vector, will ever be explicitly written down anywhere. Okay, so you only get the answer as a superposition, right? As the list of amplitudes in a quantum state that you then have to measure the state and extract something from what you see. Okay, so that's the QFT. All right. So the upshot of all of this is that factoring, or at least when suitably phrased as a decision problem, which is easy to do, is in BQP. It has a polynomial in the, time, meaning polynomial in the number of digits of your number quantum algorithm. Okay, you can generalize this to numbers that are not just a product of two primes. That's an exercise. You can, and then in his paper, Schur also looked at the problem of discrete logarithms. Okay, so factoring is the basis for RSA encryption. Discrete log is the basis for Diffie-Hellman encryption, right? Which was actually discovered before RSA, and which is at least as widely used. Okay, and but you can also reduce this to some version of period finding, and you can thereby solve that in BQP as well. And then shortly afterwards, people realized that even taking discrete logs in weirder kinds of groups, like elliptic curve groups, can also be done with Schur's algorithm. So the practical upshot is that if you build a scalable quantum computer, you break almost all of the public key crypto that is currently used. Okay, you break RSA, Diffie-Hellman, elliptic curve crypto. But it is important to understand that all of these are sort of very, very structured cryptographic problems. They're sort of ones that have an abelian group lurking inside of them, if you like. And Schur's algorithm is really taking crucial advantage of that sort of special number theoretic structure, right? That these, that these problems happen to have, right? And it's like the same, so is this all just a coincidence? Well, the same number theoretic structure that makes it possible to solve these problems with a quantum computer is also, alas, what makes them so useful for crypto, right? So like structure giveth and structure taketh away. Okay, but then since then, a major research topic in cryptography, even in classical crypto, has been to develop what we call post-quantum public key cryptosystems, right? Which are public key cryptosystems that would give us the advantages of, our current ones, like RSA and Diffie-Hellman, but that would resist attack by Shor's algorithm or anything similar to it. Okay, and there are pretty good candidates today for these plausibly quantum safe public key crypto systems. Okay, so the best known or best studied class of post quantum crypto systems are based on problems involving lattices, like finding short non-zero vectors in lattices, things like that. And this has been a major research direction in classical cryptography for the past 20 years. Okay, getting a security against quantum computers is only one of several motivations for this. Turns out, these lattice-based crypto systems also let you do all sorts of amazing things, like if you've heard of fully homomorphic encryption, right? You can do arbitrary computations on encrypted data without ever having to decrypt it, right? And so this could be, extremely useful for cloud computing, for example, right? And so, in a world where, it looks like, scalable quantum computers, like, ones with millions of qubits or whatever, were on the horizon, probably, the most obvious thing to do would be to just try to get everyone to upgrade to these post-quantum crypto systems, okay? Unfortunately, these systems are less efficient than our existing ones in the sense that they require much larger key sizes to get the same level of security, right? And that's one reason why they're not widely used today. Okay, but we could just suck that up, right? And furthermore, there's been a lot of research by now that's gone into making these systems more efficient. Okay, and they've gotten a lot better. They used to be totally impractical, and now they're more or less practical, just not quite as fast as RSA. Yeah. So I mean, for the most part, it would just be software that has to be updated, right? I mean, there are places where crypto is directly implemented in hardware, right? But usually it's somewhere in the software stack. Okay, now so like to a theorist like me, that just says, okay, so just replace the software and you're done. Okay, now in reality, when you talk to the applied crypto people, they will tell you that there are web browsers that are still using crypto that was broken in the 90s. Okay, like you can force a server to use 512-bit Diffie-Hellman that people already knew how to break in the 90s, right? Partly this is because it's like for getting people to upgrade their all legacy code turns out to be really, really hard. Partly it is because the NSA did not want people to upgrade. Okay, and this was a big controversy back in the 90s. Okay, so these are the practical aspects, if you like. Yeah. Well, it is. I would say that it's somewhat practical. It's just slower. Well, these are questions whose answers are changing with time, right? These are like literally like every year people are improving these things, right? You might need some I don't know, tens of thousands of bits of key or something, as opposed to merely 1,000 bits, right? But I'm not sure of the exact numbers. Okay. What was I going to say? Oh yeah, right. But now an important point is that the only thing that you actually need public key crypto for in practice is to sort of agree on a shared secret key, right? So like if Alice and Bob can just create a shared secret key, like in some initial phase, then from that point forward they can just use private key cryptography. right? They can use something like AES, right? Or, and for these private key crypto systems, we basically, we barely have any toehold with any known quantum algorithm. Right? So that's a completely different situation. For private key crypto systems, typically the best speed up that we know how to get from a quantum computer is simply the square root speed up that comes from Grover's algorithm, which I will tell you about this afternoon. Okay, so but if quantum computers are getting a square root speed up, then that means that you can get the same level of security by simply doubling the length of the key. Right, so private key crypto should probably be fine. It's only for public key crypto. That to get all the amazing features you want, you need to put all this mathematical structure on your crypto system. The more structure you put, the more the danger that someone like Shor will come along and give it out, either a classical algorithm or a quantum algorithm to break the thing. Okay. And people have been working for the last 20 years on trying to design a fast quantum algorithm that would break even lattice-based cryptography, right? And that would therefore destroy this escape hatch that we had. People like to study things regardless of the value to humanity. Okay, but so far so far they've not been able to. It seems like a very, very hard problem to generalize Shor's algorithm to this sort of case. And actually, if we have 5 minutes, I'll tell you something about why. But first, a question.
I guess
Yeah.
The question was kind of related because I was just wondering if there are any currently known complexity theory arguments that say that this is going to be hard for quantum.
No.
And if,
No.
but
Yeah.
But if this turns out to be something that is practical,
Yep.
then does that mean that these quantum cryptography ideas are not really?
Well, these are so it is often said, and only half as a joke, that one of the main applications of a quantum computer is to create a market for quantum crypto. Right, because quantum crypto solves a problem that is already extremely well solved by public key crypto, right? Over the existing internet, right? And so once that it is only once that becomes broken, I think that then people really practical people really start looking. Do we go to lattice-based crypto or things like that, or do we go to QKD, right? My guess is that QKD would probably be used in some specialized cases, in cases where you need super high security, or I'm not sure. It'll come down to practical considerations, but they'll both be contenders. Yeah.
What's the intuition behind lattice-based crypto to be quantum safe?
Okay, good. So let me talk about this in the last 5 minutes. Okay. All right. Okay, so I won't have time, unfortunately, to tell you about how the lattice-based crypto systems work. There's a whole enormous, beautiful theory about that. Also I didn't prepare to talk about it. Okay, but what happens at the end of the day is that when you try to break these lattice-based crypto systems, you end up wanting a generalization of Shor's algorithm to non-abelian groups rather than abelian, right? Everything, so shortly after Shor's algorithm was discovered, and Simon's algorithm, both of them were put into a much more general framework, which is called the hidden subgroup problem, or HSP. Okay? So let me just state this general problem. Now we are going to be given a black box function, f, which maps from the elements of some finite group G. I won't say which one yet. Let's say to integers or something. Okay? And now we're going to be promised that there exists what we call a hidden subgroup H of G, such that for all x and y in G, f of x equals f of y if and only if x and y belong to the same left coset of H. Okay, and now the problem is going to be, by making queries to F, as few as possible, find a list of generators for H. Okay, so this sounds a little abstract, but let's see how both of the algorithms that we saw today fit into this framework. Okay. Or well, almost fit. Okay. In the case of Simon's problem, what would be this group G? Anyone? Anyone see? What is sort of the group that is underlying Simon's problem? Huh? What? Sorry, I know. I'm asking for a group. Yeah. So it's the group of all n-bit strings, with the group operation being bitwise exclusive ORing, right? So we could say for Simon's problem just is the hidden subgroup problem in the special case where your group G is z2 to the n, right? Just sort of, the group of n-bit strings under bitwise addition, mod 2, and where your hidden subgroup H has order what? 2, right? It just consists of the all 0 string and your secret string S, right? And then, and then this is just exactly Simon's problem. Okay, you can exercise, verify that. Okay, for Shor's period finding problem, what would be the group there? Well, okay, this doesn't quite fit into the framework because for this reason that it's like, we want to be looking at now an additive group of integers, like let's say the set of all integers under addition mod Q. Okay, but now the trouble is, as I said, S might not divide Q, right? And so, the group, the set of integer multiples of S may not be exactly a subgroup. Okay, but it's sort of it's sort of close enough that if you squint, it kind of falls into this framework. Okay, now it turns out, for reasons that I'm not going to have time to go into, unfortunately, if you want to break lattice-based cryptography, then again this hidden subgroup problem comes up, but the group that is relevant now is going to be a dihedral group. So it's a non-abelian group. Okay, and now the fact that it's non-abelian somehow, makes everything a lot harder, and people have been stuck on this for 20 years. Okay, now I should say, it is also possible that someone could give a quantum algorithm for breaking lattice-based crypto without having, going through the framework of the hidden subgroup problem, right? That's entirely possible. We simply don't know. But at least if you want to follow the approach of Shor's algorithm to break lattice-based crypto, then this is the place where you get stuck, at the fact that this group is non-abelian. Okay. Now let me just end with one final exercise for you. Okay. Let's say that we looked at this hidden subgroup problem, but in the case where our group G was the symmetric group. Okay. So like the group of all permutations of n elements, right? And let's again we'll just look at So our group is the symmetric group. Okay. And let's suppose that we had a fast quantum algorithm to solve, HSP when G is the symmetric group. Okay? Show that would then lead to a fast quantum algorithm for solving the graph isomorphism problem. Okay, which is another famous problem in this that might be in this demilitarized zone between P and NP complete, right? That we don't exactly know its status. Okay, I'll give you a hint for this problem. Okay, look at the take G union H. Let's say G and H are two graphs on n vertices. You want to know are they isomorphic or not. Just look at the union of the two graphs. And now just look at permutations on a 2n element set and just look at how they act on that 2n vertex graph. Okay? See if that gives you a function f that satisfies the assumptions of the hidden subgroup problem, and such that finding the hidden subgroup would then tell you, or finding the generators of the hidden subgroup H would then tell you whether G and H were isomorphic or they were not. All right, so that's the HSP. We'll continue this afternoon with Grover's algorithm, and then if we have time, the collision problem, quantum machine learning. Yeah, thanks. You had a question? Yeah. Okay. Good. Right. I didn't develop enough theory to be able to really explain that. So basically, the Fourier transform, is a much simpler thing when you're doing it over an abelian group. That's the short answer, right? So you can, for any abelian group, you can define a natural Fourier transform, and then, you can show, that given the measurement results after applying it, that you can actually get enough info to solve the hidden subgroup problem. For non-abelian groups, there also are Fourier transforms, but they're more complicated things where now you have to worry about representation theory, right? And as soon as it becomes representation theory, then you know that it's hard, okay? Or at least I know that it's hard, and that I'm not going to fully understand it, okay? So so for a few very special non-abelian groups, people have managed to generalize Shor's algorithm to handle them. Typically groups that are very close to being abelian in some sense, okay? And for most of them, they just don't know what to do. But actually, there's a very beautiful observation due to Edinger, Hoyer, and Knill from 20 years ago. Maybe I'll just end by telling you this. What they observed is that regardless of the group G, if it's abelian, non-abelian, no matter what it is, the hidden subgroup problem for G always has small quantum query complexity. Okay, so there is always a quantum algorithm for HSP that only makes, let me write this. There is always a quantum algorithm for the HSP that makes a polylogarithmic in the order of G number of quantum queries to F. Okay? But this is an instance where query complexity and computational complexity seem to diverge. Okay, so even though there is a quantum algorithm that makes few queries, the algorithm that they gave requires an exponential number of gates to sort of interpret the results of those queries, and no one has been able to figure out how to do it with a polynomial number of gates for a general group. Yeah. Yes. Yes, it is constructive. They do give an algorithm. The only problem is the algorithm involves taking some quantum state and then repeatedly measuring it over and over an exponential number of times. So, so it's not an efficient algorithm. That's the issue. Okay, but it's a beautiful result. And if I had time, I would prove it for you. But, if you're interested, you should go read their paper. Yeah?
Since we found out recently that graph isomorphism is classically quasi-polynomial time, it seems like a less tempting target for a quantum speedup.
I agree, completely agree. I mean, look, people had been attacking this, find a fast quantum algorithm for graph isomorphism for, 25 years, like a Moby Dick, right? And they just, would just bang their heads, like people like spend entire like careers, on this problem. And I would always like look at this and say, wow, like I guess I'm happy that, I don't know, some people like, impale themselves on this problem, right? But it's, graph isomorphism is just, we don't know enough about graphs, right? And, maybe it has a fast quantum algorithm and maybe it has a fast classical algorithm, right? It just, we don't know enough about graphs. Reducing it to HSP over the symmetric group, that works, but that's throwing away an enormous amount of structure that comes from graph theory. Right? It's just, why would you do that? If you want to attack graph isomorphism, know something about graphs. So anyway, so that is what happened. Lassie Babai does know something about graphs. And, he worked on this problem for 40 years. Ultimately, just a couple years ago, coming up with a classical algorithm that solves graph isomorphism in n to the polylog of n time. Which now means that the best you could hope for with a quantum algorithm would be to, improve that to be truly polynomial, which, maybe you can do it. But again, maybe you can even just do that classically. Okay. I don't want to cut into the break too much. Yeah.